How you doing? I'm Mr. Rose, and today we're going to give you an overview, a start to finish of everything there is to know, relatively speaking, of work and energy. So the way we're starting this today is the first thing we're going to do is we're going to define what work is. Now, work in its simplest definition is essentially the measure of how much energy transfer when an object moves from one place to another, so when an object moves over a distance by some external force. Now, some caveats to that. The force applied does need to go in the same direction as the object is moving, otherwise known as its displacement. So, when we were younger, as perhaps freshmen, if you've taken a freshman physics course, we learned that work, very simply, was just a force times a distance, right? Now, we're getting a little bit bigger, a little bit better in our understanding, so this force times distance is actually a little bit incomplete. We now are going to start to understand that work is actually a scalar dot product. Now, we're going to come right back to that in a moment, but a scalar dot product is a way of multiplying vectors. And in AP physics, we use this general R as a displacement. So we know work, again, thinking about that definition, is really some force dot R. That's how I say that. Force is F dot R, which is equal to FR cosine theta. Now what this is going to tell me is that the force and there's some part of R in the same direction as F, and that's a function of the angle in between F and R. So here I have a little bit of a diagram, right? And here's the sun projects some light, and I have vector A and B with this angle theta. Well, if I want to take a dot product, a scalar dot product, multiplying two vectors using this, A and B, this sun is supposed to represent kind of like a shadow, right? So A is going to cast a shadow, which I've called A prime. So this scalar dot product essentially is like a projection or a shadow, such that B and now A prime are in the same direction, where A prime, this isn't a prime like calculus, it's just another designation, where A prime is equal to A cosine theta. So if I had this scalar dot product, it would be B times A cosine theta. So that's a real kind of simple definition of what the scalar dot product is, and we're going to relate that to doing some work. Because again, in smaller or younger classes, we always have forces going in the same direction as motion. Here we're going to have a little bit different thing. So we first need to know that doing a dot product for work and any dot product, when I multiply these two vectors, again I call it the scalar dot product, because the function of that, the answer of that, is always going to be a scalar quantity. So work is essentially a scalar quantity. Let's look at an example. Here I have a simple diagram of what I've written over here. So I have some force of 4.2 I plus 3.1 J Newton. So I have some force in some random direction. And it's going to move 5.5 meters in the J hat direction, which is straight up in the Y direction. Now notice I have no angle here, so FD cosine theta isn't really going to help me. But the dot product is multiplying vectors, and here I have two things in vector form. Now, when we use a dot product, and we do have some knowledge of sines and cosines, I can maximize and minimize sines and cosine. In other words, when I have the cosine of 90, I know that's 0. That goes away. When I have the cosine of 0, 180, that's a maximum or a minimum. So when I multiply or do the dot product of my force and my delta x, I'm really going to multiply 0I, there's no I component, times 4.2I, plus 5.5J times 3.1J. Now, I hat and I hat, that's I and I, those are unit vectors, that multiplies to 1. So I would have this 4.2 times 0, that actually doesn't matter. But then this 5.5 times 3.1, J hat times J hat, those J hats cancel, or essentially equal 1. So I'm going to write all this out now to show us what our answer is. And now here you can see my work. As I said, work is F dot R, and I have my force and R. Now I didn't have room, but this would be 0I, which is why I have here 4.2 times 0, I dot I, that's my 1, and that cancels out. 3.1 times 5.5, that comes out to 17.05. And again, just because of space, I don't have my newtons and my meters, but I know them in Newton meters, so my unit for work is a Newton times a meter. Now again, notice I didn't need the angle theta there, but if I had it, it would have been a little bit easier, and I don't necessarily need to have all of my unit vectors. If you wanted to, you could have attempted to find the angle and do it that way. I didn't do that because I kind of thought it would be a waste of time. So the other thing I want to point out is all of this work happened because of the forces, the essential projection of the two forces in the I hat direction. In other words, that is the J hat direction. This 4.2 I hat had nothing to do with the work actually done because that I is in the X direction. So you saw me grab my calculator. If I'm just holding my calculator up here and it's not moving, I'm lifting this force up, but I'm not doing any work. Even if I start moving it side to side, I'm moving in the X direction but not the Y direction. So whatever force I need to lift that up is not actually accounting for any work that I'm doing on the calculator. So that kind of gets us through this little bit of work. Now, here I have the unit of work is a Newton meter, and some things to clean up. 1 Newton meter is going to be, if you recall, the same thing as 1 joule, which is a capital J, and that is going to be the same thing as 1 kilogram times meter per second squared. Actually, meter squared per second squared. Yeah, that's right. 1 kilogram meter squared per second squared. So these are all the accepted units for work. Now, if we move on here, this is all well and good if we have a constant force. What if I don't have a constant force? In other words, if I look at my AP sheet, I see this weird antiderivative sign that I know we all come to love. So sometimes force is not actually constant. And if F isn't constant, then I have my change in energy. Again, let's go back to that definition. Energy transfer, so that's the change in energy, is work. And work is an antiderivative of F dot dr, where F and dr are constants. Now this dr is some very, 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 very small r, some very small displacement. I sum all of those up and I would get F times r. Now this is an indefinite integral. We need to remember that, which means if I'm doing something like this, I need to have that plus c, or my integration constant. If I have a definite integral, if I know I'm moving it from point A to point B, then I have an initial and a final position, and I can equate an exact answer. Now, this means right now I've essentially just introduced two equations for the same thing. I've introduced an F times D, or a really F dot, let's get this out of the way now, an F dot dr, and I've introduced this antiderivative. Now, it's not really two equations, it's actually just one, because this integration will always work. It's a stronger equation. The reason why I sometimes don't need it is if F is constant, as I've written out here, constant force, that force just comes out of my integral, because it's a constant, it doesn't matter. So I can pull that out of my antiderivative, and then I just have F times the antiderivative of dx. When I take the antiderivative of dx from an initial to final position, it's just F times x. So they're kind of, they're definitely the same. This is a more powerful equation. You don't ever need to memorize both equations. Now, I also want you to remember that these antiderivatives are always talking about the area under a curve, what might be important in the future. Also, by area under the curve, remember, we're not just talking about under a curve, we're really talking about the area that is between our graph and our x-axis, depending on if the graph is on the positive or negative side. So, that's kind of my big introduction to work, and to move forward, we're going to now start talking about Hooke's law. Hooke's law is also something that's important in work and energy. Now, Hooke's law is related to the force and or energy required with a spring. So it's really talking about the force of the spring, and I have Hooke's law equation equals Fs, that my little s is for the spring force, is equal to negative k times a change in position, change in x. So let's talk about some of these variables first. My k is something called a spring constant. A spring constant going to use this spring in a moment. The spring constant is either how hard it is to stretch or if the compression string compress my spring. So that's what K is. And you can see by inspection, if I bring that X to the other side, the unit of K is a Newton per meter. Now this delta X is again going to be its displacement, but now it's a little bit different. This delta X is essentially how much, if you can imagine this is a system, and I got this big yellow rag so you can kind of see it. Now if I go from an equilibrium position, and this is a stretch spring, so I stretch it, my delta X is how much the spring is either stretched or compressed from equilibrium. It does not matter if it's horizontal or vertical. Its equilibrium position to its stretched position or compressed position is always going to be our delta X. Last is this negative sign. Now this force is the force due to a spring. So as I am pulling on my mass to bring it, this is a restoring force, meaning I'm pulling it towards my right. The restoring force is in the opposite direction of displacement. That's the purpose of the negative sign. So that's this little equation in in a nutshell. Now the question is this force constant? Right? Here's my question. Is my force due to a spring a constant force? In other words, as I stretch more and more and more, is that force the same force, increasing or decreasing? The answer, it is unequivocally not a constant force. Okay, so now with a little bit of editing genius, I think it's very dark. I'm going to take my hat off with my hat head here. We're back at the front of the room here, and now what we're going to do, as I said, the energy of a spring is, the force due to a spring or acting on a spring is not constant. So we need to use some calculus. You can see here I have set up 1, 2, 3, 4, 5 steps. Now this is going to be my final equation. See if you can derive on your own the work done on a spring. And we'll see if we match when we're done. All right, so let's see how we did here. I plugged in my negative kx for my equation for a spring. This k is a constant, so I pulled it out. So I have the antiderivative of x dx from my initial to final position. I have negative k, that didn't change, of x squared over 2. That is the antiderivative of x dx from my initial to final position. Then I wrote this in blue. You might remember this. The work or potential energy of a spring, we're going to come back to it, 1/2 kx squared. That is at a specific point. And this is something that we may have seen in an earlier physics class. And again, we're going to come back to that. Now plugging in, I had my negative kx squared over 2 minus negative kx 0, my initial position squared over 2. Way too many negative signs to deal with, so I factored some out. And I have a negative kx squared over 2 minus k naught squared over 2, which is now recalling my definition of energy. Of work. Work is the change or transfer of energy. So that's all that's happening here. So in this final blue equation, like I said, I'm going to come back to this later. Earlier in an earlier physics class, we may have known the potential energy of a spring, 1/2 kx squared. Here we just proved that. We have negative kx squared over 2 minus kx naught squared over 2. By definition, that is a change in energy or elastic potential energy. So here I have a negative elastic potential energy. U is our potential energy. I have a little sub E as my elastic. So I have a final elastic minus an initial elastic potential energy, or a just change in elastic potential energy. So this is again coming back from earlier physics classes. We're just building on information. Now obviously if I'm moving this spring, that's going to get us into moving energy. I'm sure you recall moving energy again from an earlier physics class as kinetic energy. Well, I'm not even on the screen. As kinetic energy. There we go. So we have a work kinetic energy theorem, or a work energy theorem, but here we're going to talk about specific kinetic energy. So as I come over here, we have a simple proof that we can get work into some change in kinetic energy form. Again, I want you to see if you can do this. Now, we may remember the formula 1/2 mv squared, and that's what we're going to try and get to. So to simplify this a little bit, we made some assumptions. First of all, I'm going to assume a constant force because it's easier. And again, here's a couple of hints. We're going to use this work formula. And I'm going to deal with some constant acceleration or some kinematic equations. Again, see if you can come up and do this on your own and see if we match when we're done. So here we can see that, get out on the screen here, here we can see that I started with work and I subbed in at MA for force because that makes sense, and my delta x is just x minus x naught. Now I said I was going to use some constant acceleration equations, and I chose v squared equals v naught squared plus 2a times x minus x naught. And I mean, I knew where I was going. You might not have chosen this right away. I simplified a little bit, and as you can see, I underlined a x minus x naught, so I made a substitution. So using my substitution, I have work is mass, which I have mass, times what I have is a x minus x naught is v squared minus v naught squared over 2. Now I can distribute my m, and I have my work is equal to 1/2 mv squared minus 1/2 mv naught squared. And if my v naught is equal to 0, I have my simple kinetic energy equation, or my work kinetic energy theorem, as just the work is a change in kinetic energy, and kinetic energy is 1/2 mv squared. Now again, we can do the exact same thing if we're going to try and find potential energy. Again, potential energy is U. What I would like you to do is, again, try to see if you can do the same thing. It's going to be the exact same method to try and find your work potential energy theorem. Now, this one's a little bit easier. I have work equals force times the distance. Now, I should really use a y because potential energy is in the y direction. Here, I'm just trying to be consistent. We've been using x all day. So here I have work is equal to F times my change in x. And my change in x is just x minus x naught. And force, since I'm lifting it up, is going to be that mass times gravity. That's the force I need to lift. Simple plug and chug. I get my work is mgx minus mgx naught, my final minus my initial position. If initial position is 0, then obviously I have just mgx, mgh, or mg delta h. Now, with potential energy, it's always very important that you define a starting point. We need to define 0 all the time. If we don't, for example, right now I'm standing on the 2nd floor. I have 0 potential energy. You hear me stomping on the ground. But if there were people underneath me, if I was standing on a glass floor, which I'm not, and they looked up, they all of a sudden flinch because they think I'm going to fall on them. So the people underneath, I have a potential energy with respect to them. So we always need to define a starting point or a 0 point for our energy purposes. We're almost done. Just bear with me. All right, so to continue our very long lecture about everything we need to know about energy, work, and power, we are now going to talk about isolated and non-isolated systems. An isolated system is when the change in energy of the entire system is 0. In other words, there's no energy going in or out. You indefinitely are right now a non-isolated system because you have been losing energy as this lecture is dragged on and on and on and on. So there's energy leaving that system. Terrible physics example, but hopefully we get that idea. In a non-isolated system, the change in energy is the sum of all the energy that enters the system or leaves the system. So if I'm continually adding energy into the system, I've got all this energy now. If I'm continually adding energy into the system, it would be non-isolated. Now, where it gets a little weird is when I have something dragging across the floor, for example. I can deal with friction. If we're not ignoring friction, I'm still going to consider that an I guess I should say I still can consider that an isolated system, even though I have what I'm going to call a non-conservative force. Friction is a non-conservative force as opposed to a spring force or gravity, which is conservative. Well, what's the difference? A non-conservative force is when I lose energy, because we have conservation of energy. When I lose energy, in other words, I can't get it back. Gravitational potential energy, all the energy I put into the system, I can get back out of the system. So friction or air resistance, another type of non-conservative force, really those are only two that we ever talk about. Those are non-conservative forces that we can still consider in our isolated system. So often we'll call that non-conservative force internal energy. And a change in internal energy would be a negative non-conservative force because as I drag something across the floor, in other words, if I know that I put 15 joules of work into something, but I can only measure 10 joules, Friction took 5 of those joules. That was a negative, negative energy, or energy leaving that system. When we have conservative, non-conservative force, we need to talk about path dependence. Now, if an object is an isolated system, that means it is path independent, or if I have no non-conservative forces. So I have path dependence when, I have a non-dependent track if my change in mechanical energy, or I have no non-conservative or no work due to friction. My change in energy will be 0. If I have a non-conservative force like I have to deal with friction, then my track that I'm moving something becomes path dependent, because the further I go, the more energy that would take. Very simply put, really it doesn't actually matter if it is conservative or non-conservative, though some things get more complicated. We always have this conservation of energy. Conservation of energy means energy before has to be equal to energy after. I will say very often, especially as we get further on in this course, conservation of energy and conservation of momentum are the 2 most powerful things in Newtonian mechanics. And they both will always work. But to use conservation of energy, you need to be a better accountant. You need to know where all this energy is going. Our change in total mechanical energy is always going to be our final energy minus our initial energy. If it's an isolated system, that change is going to be 0. It doesn't matter what kind of energies we're using, kinetic energy, potential energy, elastic potential energy. Here's a nice simple version of my change in total mechanical energy. I have my final kinetic plus my final potential. I have my initial kinetic plus my initial potential. We have to subtract those 2. I have my non-conservative forces, or my non-conservative work, rather. I subtract all that, there should be a change of 0. So in order to do that, we need to understand in that isolated system, again, we never have that change in energy, or energy before equals energy after. That's another way to say it. In order to use conservation of energy, we usually need to know 3 things. That's the initial position of an object, the final position of an object, and we need to know where it starts. It's 0 or its starting point. Now, that gets us through almost everything about energy. Next, we have to talk about power. Power, the equation for power is nice and simple, work divided by time. Now, this is an average power, and it's also the definition. It is a change in energy or change in work per unit time, the rate at which work is done. This is an average. Then we get to our calculus stuff that we know, a dW, a very small change in energy, very small change in time. This is our instantaneous power. Power, we can see, is a joule per second. That's also called a watt. And here in AP land, we talk about power as a change in energy per unit time. So a very, very small change in energy per very, very small unit of time, or an instantaneous change in energy per unit time. Now here I've rewritten power as, again, a change in work, a dW divided by dt, and we get to do some kind of cool things with power, right? I know that work in its simplest form is just F times x, or change in x, which means I can rewrite this. Here's my derivative, my d dt, and I'm just substituting in force times x, fx, for my work. Now when I do that, if I assume force is constant, for this I'm going to just say let's assume force is constant. If I assume this force is constant, I can pull that out, and I have f times dx dt. Dx dt is just an average velocity, which means I can also have a power with a constant force times an average velocity, which is also a very powerful thing. This is how I get, like, engine power, a horsepower. 746 watts, I think, is 1 horsepower. Now, here I have power is my change in work divided by time. This we know is a derivative. Anywhere there's a derivative, that, sorry, my eye was twitching, that also means there could be an integral. Now, we will say very, very often, or integral antiderivative, that this dw dt is not a fraction, but for reasons that will be explained in calculus, we can kind of treat it like a fraction, and I can multiply both sides by dt. Now I have power with respect to time is equal to a change in work. Now if I take the n, a change in work. Sorry, I got a little crazy there. If I'm looking at this, and I remember that antiderivatives, I said this earlier today, an antiderivative is just the area under the curve. If I just sketch some curve there and highlight all that, if I did some calculus, I should drop my marker on the floor, and I should be able to, if I just want to do simple area, say that that is a change in work. So that area under the curve is really my change in work. Now, we're almost through this. Last thing, everything we do, unfortunately, does not live on the AP formula sheet. In its simplest definition, a conservative force. When we have a conservative force, that is change in energy or potential energy per unit time. Now, if I look at a spring here, we're going to be able to derive Hooke's law with this simple definition. This is factual. It's a negative change in potential energy per unit time. So if I plug in the spring energy here, so I'm going to say Fs, we're able to take that definition, everything that doesn't live on the AP sheet, my negative change of potential energy per unit time, and derive my Hooke's law, Fs equals negative Kx. We can do the same thing with gravitational potential energy, and in fact, I recommend that you try and do that to see if you can take this definition, know that potential energy is mg times delta y, and see if you can derive your force, or essentially your weight. We should end up with F equals mg. Again, I highly recommend you try and do that. The very last thing we have are three equilibrium states. We have a neutral equilibrium, a stable equilibrium, and an unstable equilibrium. Now, I'm going to grab a different color. A neutral equilibrium is going to be, here I have three axes that are all the same. My gravitational potential energy is on the y, my x position is on the x. Neutral equilibrium means nothing's happening, essentially like a ball rolling on a plane. So if I throw a horizontal line there, this would be a graph that represents neutral equilibrium. In other words, as I change my x position, nothing changes in my y direction. Neutral equilibrium. Stable equilibrium is going to be a parabola. A stable equilibrium is something that looks like that, which means as I change my x position, I'm going to have an increase in gravitational potential energy. This is really raising the center of mass of an object. So all of us have sat in that chair and balanced and tried to balance, and you got it, you bounce for a second, slam, you slam forward. You usually don't fall backwards. That's embarrassing when that happens. But that is an example of stable equilibrium, is where you're balanced, you're increasing your potential energy because your center of mass is changing, but then you slam back to that stable point, all four legs on the ground, that stable equilibrium. An unstable equilibrium is the exact opposite. An unstable equilibrium would be something that looks like that. Now you can picture, if I know this is silly, but this is a graph, I pictured a ball here, it would roll off. Or, actually, if I were to try and balance this marker, and then I just give it a little nudge, as opposed to the chair that comes back, if I gave it a little nudge, I can't balance it, so I'm not going to try it, it would fall straight over. That is unstable equilibrium, meaning as I get further from the x-axis going out, my center of mass is going down in that case, thus we are losing potential energy. Now, that is everything we have about energy, work, and power. Please feel free to like, click, and subscribe, assuming you're on my YouTube channel. Bring me comments and questions, and that's all I have for you. I'll see you next time.